Hello. Think I'm ready. Okay. Do you see the desktop there? Can you hear me? Does everything seem okay?
Yes.
Can you hear me? Does everything seem all right?
Yeah, it seems fine.
Oh, I have my speaker turned on. Okay. I got my speaker turned on. Is it, can you hear me?
Yeah, you're
Yes.
good.
Okay, great. Now I hear you too. All right. All right. Okay. Okay. So first, I put two links up here that are semi-relevant to what we're talking about. The trouble is they're very good references, but they're to different languages. So like this one is a real nice explanation of higher order functions using JavaScript. It's really well written. In fact, this is a great book. This is a free book about JavaScript that's available online. You can download, you can read it online. You can download a PDF of the book. You can buy the book if you want it. You can buy it on Amazon or any It's a great JavaScript book. It's probably the best one out there. So there's a nice chapter in there on higher order functions because JavaScript is leaning in this direction towards functional programming. Okay, and if you look at the table of contents, it's a very this book is all kinds of JavaScript programming. Like in this case, this chapter is emphasizing the more modern object functional programming aspect of JavaScript. This is more object oriented. Then other stuff just is web programming. Like this is asynchronous programming and event handling is very much JavaScript as writing applications for the web. See, here's a chapter on HTTP. It's a very, very good book, really good book, really well written. Okay, so it's got a nice explanation of higher order functions, but it's in JavaScript. So you can read it, and JavaScript looks a lot like C and C++. If you've never worked with JavaScript, it's not hard, while, count is less than 10, console.log is just the same thing as system.print. Okay, so it's not hard. See, you can run the code directly in the web pages. See how I ran that code and it printed out the answer. If I want to change, I can change the code and rerun it. See, change the answer. It's really nice. The book is interactive. You can run code right in the book. You can play around with code as you're reading the book. Okay, so that's one. If you're interested, especially if you're interested in learning some like comparing the idea of higher order functions ubiquitous. It's in every language. So we're learning it in ML in this case, but it's available. It's in Java. It's in JavaScript. It's in C++. It's not. It's kind of in C, but not really. But people don't do this kind of programming in C. Okay, and then here's another explanation of higher order functions. But this is a dialect of ML. It's not ML itself. It's in a language called object-oriented ML. So it's called OCaml. Okay, the O stands for object-oriented. I forget what the CA stands for, but it's a dialect of ML. So everything is written a little bit differently. Like you use the word let instead of the word val. So instead of saying val, you say let. And there's a couple other little differences in the language. So you can kind of read it, but you have to get a little bit used to this slightly different dialect of ML. But it's also but the book is really good. The book is a very good book about the OCaml dialect of ML, and it's got kind of a nice explanation of higher order functions. One thing that's kind of interesting to notice is that in this chapter from the JavaScript book, the first thing he talks about is abstraction. And this other book, the first thing they talk about is abstraction. That's the computer science idea that higher order functions are all about, is a better abstractions to program with. So they both lead off with the idea of what's an abstraction. Why is higher order function an interesting abstraction? And you can see that that's a good computer science concept to think about. What do we mean by abstraction? Why are higher order functions? Here's the table. Why are higher order functions a good example of an abstraction? Then see here, map, filter, fold. Okay. And in this book here, he also does, if you go through here, he goes through filtering, map. He uses the word, JavaScript uses the word reduce rather than fold. So JavaScript uses the more old-fashioned word reduce. So filter, map, fold. Okay. So I, I think those are really good explanations. I mean, obviously they're not for this class, so they're not required reading, but I think it's, especially this JavaScript book. If you're interested in learning some JavaScript and you're wondering like, where's a good place to learn it from, that's a really good book. And if you do know JavaScript, that's also a really good book to look at because it has its own, it does a, it explains things in a really modern, good computer science way. And also has really good projects. Uh, the drawing on a canvas, uh, implementing a simple programming language. Yeah, it has a little introduction to Node. It covers a lot of good ideas and just does a real, and it has these projects. In the book are these kind of major programming things where you write like a fairly substantial, he shows you how to write something more substantial than just the little examples. So there's a couple chapters that are projects that are kind of, it's a nice idea to switch from just talking about simple examples to saying, here's how you'd write a whole program. So he's got, I think, 3 or 4 chapters where he does a more substantial project. Okay, really good book. Okay, and it's not even expensive. It's not even too expensive a book if you want. If you like reading physical books, if you buy the physical book, it's not even all that expensive to buy the physical book. So it's one of these people who's not writing a book to make lots of money. You know, he makes the book available for free. You know, someone who's very much in the modern open source movement. So even his book is available for free, though you can buy it from the publisher is this company. It's a company that prints really good. The other thing that's interesting in this book is the publisher. Okay, this is on Amazon. See if I can get the publisher, because the publisher is a really interesting company in their own right. Here it is, No Starch Press. This company prints really interesting books. Uh, they write a lot of books that are like introductory books on programming, especially on Python and JavaScript. And there's some examples of their introductory books. They write really nice books. Some of them are free, not all of them. Some of them are free. Some of them you have to, you can only get them by buying them. So some of their books, like the Eloquent JavaScript, the author chose to make it free, and the publisher will sell it to you, but the author chose to make it free. Like this is another one. This is about the Haskell programming language. That book is also free. You can read it over the internet, or you can buy it from them if you want a physical book. Okay. Yeah. Here's a book on computer graphics. You know, this company emphasizes introductory books, but not in a real textbooky kind of way. You know, they emphasize uh, introductory books that are kind of fun. A lot of them are geared for high school even. A lot of their books were really meant for an interested high school kid to learn about it. But some of them are actually quite sophisticated. Like this book here is a really good introduction to visualization using JavaScript. Kind of a well respected book in its own right. And then this is a book. This is the introductory book on the Rust programming language. That book is available for free, but you can buy it from them. But that book is written by the people who invented Rust. So it's the book on the Rust programming language. So they do all kinds of neat little books like Mission Python, books that are more fun and geared towards introductory programming. A lot of books on writing games. Yeah, very interesting publisher. Yeah, when you go through this page here, you don't necessarily know which books are free or not. Like they don't really tell you which one of these are free. So if you want to know if one of their books is free, a lot of times you have to Google the book to see if it's if the author himself made it available for free. Okay, but it's a really interesting company. Okay, so I think it's nice for you to know about which publishers are out there doing interesting things. A lot of people read these books for fun. You know, they're just good ways. They're actually meant. Their goal is to write books that are kind of fun to read in terms of learning to program. And some schools would use these. Some of these books can make good textbooks, but most of them were meant to just be kind of fun. Okay, So this book is not so much meant to be fun. This one's meant to be a good introduction to JavaScript. So it's not written in a lighthearted or kind of funny way. It's a pretty serious book, but it's really good. Okay. All right. And then this other book is just a textbook on ML. It's actually written at Cornell. It's used for teaching their course. It's used for their course on ML at Cornell. They make the book available for free, but it was written by their professors, and it's the book they use for teaching their course. Okay, and it's a pretty good book on. Unfortunately, it's a slightly different dialect of ML. It's readable from our point of view because there's not you learn a couple little tricks. There's a couple little things that translates ML into camel and back and forth, like using let instead of val. And otherwise, their languages are they're the same language, just slightly different dialects of each other. Okay, so I just wanted you to kind of get a sense of where you can get other information and see where other people are writing about things and how they describe things. There aren't actually too many really good books. There aren't any really good books on ML. All the good books on ML were print books that didn't make it to the internet. There were books. ML was very popular back in the 90s. There are really good books on ML, but they're not free and they're not on the internet. I mean, you can find them if you know what to look for. You can find pirated copies of them, but there aren't any really good online ML books. There are some online ML books, but they're just okay. And the best ML books were written in the 90s, and there's still nobody made as far as I know, nobody made any of them free. Yeah, otherwise I would point you to them. I don't know of any. Maybe I'll put up a list of online ML books later. There are probably at least half a dozen decent online ML books, but they tend to be a little bit more advanced. They're not necessarily good. They're not as introductory as these two are. These two were meant to be first books, really from scratch. This one teaches you programming using JavaScript. The book actually thinks of itself as teaching programming using JavaScript. Okay. And probably it's not the greatest book. If you've never programmed in any language, it might be a little too hard of a book to read. Yeah, it probably doesn't really work well as a teach you programming book. But if you know a little bit of programming, it's a great book on JavaScript. Same with this one. This one's not meant to teach you programming. It's meant to teach you ML. So this one supposes you know programming, but it is meant to be it doesn't assume you know any functional programming. It doesn't assume that you've had a lot of programming. It's a pretty low level OCaml book. Okay, some of the online ML books are very advanced. They assume that you know a lot of functional programming. They just want to explain the ML language to you. And like I say, the good introductory ML books, as far as I know, none of them are free. They're just they're older books, and they kind of even the authors who wrote them, I don't know, maybe the publisher didn't give them permission. They were written before the internet was really around, and the publisher owns the book, and probably the publishers are just refusing to give the authors permission to put their books online. Okay. Okay. Now, all right, so now we're doing these examples of higher order functions. So these are this is the list of all the problems. Okay, so I want to do the ones today using map and fold. Okay, so we did a few the other day, and we want to do a few more, and this will help you get started with the current homework assignment. So let's do a few of these, and then we can look, and then we can see if let's do a couple problems using map and fold. Then we'll look at the homework assignment and see if there's any questions about that, where maybe what we did today can help you understand what's in the homework assignment. So let me see. Let me download it. And I'll just unzip it. But I want to first, before jumping to it, let's do a couple examples using fold. Okay, so here's the problems. Okay, so here's the problem. Let's do this one. Use map to write a one-line function, max pairs, that takes in a pair of ints and gives us it takes a list of pairs of ints and returns a list of ints, where it's supposed to pull out the max of each one of these pairs. So in the output list, there should be the max of each of the input ones. So yeah, if you could write a test case, max pairs of the list 2, 3, 5, 6, 1, 0. Whoops. Yeah, that should give us out the list 3, 6, 1. Okay, so that would be the test case. Okay, the output from this function should be that list there. So we can write our test case. Okay, now the key to map is that it applies some function to each item in the list and gives you out an item. Yeah, so this is the output from our function on that item. Then this is the output of our function on that item. So we're going to get max pairs takes in a list of pairs. And what we're going to do is we're going to map some function on the list of pairs. Okay. We're going to map a function. Again, we have to think about what function it should be. We want to map some function on the list of pairs. So we want a function that we want something to map on that, map on that, map on that. Now, what we want is the max of these two numbers. Okay, so the function should take in a pair. I'll call it A, B, and it should give me back the well, I'll use the. It should give me back the max of A and B. Okay, so the function will take in a pair A, B, and give me back the max of the AB. Now the max function is in ML, it's in the int package. Okay, so I use the int max function on AB. Okay, I can't remember if int max, let me check. I can't remember if int max takes its variables as separate values or if it wants them in a pair. I don't remember if int max, which way it works. So here's what I'll check. I'll go over here and I'll ask ML, what does int max do? Okay, and it tells me it's a function that takes in a pair of ints, not int, but a pair of ints. So I couldn't remember if it took in int, or if it took in pair of ints. And it took in pair of ints. Okay, in fact, notice that I'm having this function takes a pair of ints and applies that function to the pair of ints. This is kind of redundant. In fact, I could just say map. I'm going to write this real abstract. Map int max on my pairs. That's the whole thing. Map that function on my pairs. So then it'll apply that function to that pair, give me 3. Apply that function to that pair and give me 6. Okay, so let me go ahead and check this. Oops. My copy and paste key didn't work again. Okay, there's the function. And then here's the test case. Whoops. Do I have a misprint in there? Oh yeah, I have a brace here instead of a bracket. Okay. So that was supposed to be up. Oh, let's see what I do wrong. Did I misspell something? Oh yeah. Case up, yeah, case matters. Yeah, I forgot so okay, true. So I got the output I wanted. Okay. Now again, compare the two versions. Okay, there's the real terse way to write it. But yeah, if you're new to this, it might be helpful to even think about what I'm doing is I'm mapping a function that takes in a pair and gives me out the max of the pair. That's the function I'm mapping onto my input list. So my input list is pairs. I'm mapping this function on the pairs, okay? But, notice if you look carefully, you see that the function took in a pair and applied that function to the pair. So there's actually kind of a redundancy there. That's my function. I'm just I'm turning this named function into an anonymous function by saying, take in AB and apply int max to AB. But max function already has a name, so I could just map the max function on the pairs. So if I want, I can think of it this way, because this is more useful. When you're learning map, you have to remember that you're mapping a function onto a list. And here, the function already has a nice name to it. So there's the function that I'm mapping onto the list. Okay, let's look at another one. Okay. This one, I want to take, well, now it's going to be multiply pairs. Let's see. Oh, multiply pairs. Okay. Let's use that as, let's write the test case. Multiply pairs will give us, well, 2 times 3 is 6. 5 times 6 is going to be 30. And 1 times 0 will be 0. Okay. So multiply pairs is going to, it's going to be on a multiply pairs on pairs is going to be map some function onto the pairs. Okay, what function are we mapping? It's going to take a pair and compute the product. So the function is going to be a function that takes in a pair and gives us back the pair multiplied. Okay. Okay. So we're mapping the function that takes in a pair and multiplies it. Okay. Let's check that should be, let's see if I make sure I didn't do anything wrong in typing it in. Okay. And then do the test case. True. Okay. Now, notice I'm not doing very much here. The function of AB is just the product of AB. In fact, I can do the similar kind of trick that I did up there. I can make this thing even shorter by doing the following. What am I mapping onto the pairs? I'm mapping the function that is the multiplication operator. Here it's written in operator notation. So all I'm really doing is I'm switching from function notation to operator notation. But ML lets me do that by writing op star. That is now the function made up out of that operator. So ML does that for me automatically. So I can write this thing real briefly like this. I'm mapping the multiplication operator on my pairs. So I can go over here and see that, oh, that's acceptable too. And then I can do my test case. It's still true. Okay. So it's just it's a more terse way. Some people prefer seeing it written out this way. And a lot of ML programmers, they'll prefer this. The fact that what I'm really doing there is this is just taking the multiplication operator and writing it in function notation. Okay. But ML does that for you automatically. This means take the operator star and turn it into a function. This is a function in ML that takes an operator and turns the operator into a function. Essentially does this out of it. It takes the operator and makes a function out of it. Okay. And that's because you can't do this in ML. I can't just say map star on the pairs. See, that won't work. That's essentially what I'm really doing. I'm mapping multiplication on my pairs, but that doesn't make sense to ML. Star isn't a function, it's an operator. So I have to say, well, I want to map the operator. I want to map the function made out of the multiplication operator. I'm mapping the function that's made out of this. Essentially, that's just doing this for me automatically. Okay. Now, the key to map is if the input list and the output list have the same length, you're likely to be able to use a map, because map goes through the list one step at a time, applies a function to the first item, a function to the second item, a function to the third item. So the resulting list is always the same length as the input list. If somebody gives you a problem where the output list and the input list could have different lengths, it probably can't be map. Well, it can't be map. Map only works when your output list is exactly the same length as the input list. Okay. Let's see. Let's skip one. Let's try one more. Okay. This is going to be a function that takes in a list and duplicates every item in the list in a pair. See, so it takes 1 and gives us out the pair 1, 1. Takes 2 and gives out the pair 2, 2. Okay. So there's our test case. I'll put it down here as a test case. Okay. So what are we doing here? Function on x's is we're supposed to map something on the x's. The question is, what are we mapping? What function takes this and gives us this? Okay, so it's a function of x that gives us out, well, it's pretty obvious. It gives us out x comma x. See, the function takes an x and just gives us the pair xx. Okay, so that's the function that's the function I want to map onto my list. Okay, so in this one, there's no shortcut for it. That's the function. So, okay, that looks good. And then here's the test case. Okay, true. So the output matched the output we got was the desired output. Okay. Yeah. And if you want, you can just instead of you can actually look at the output. See, it gave us what we want out. You could give it more input. Okay. You could try, it's a polymorphic function, so it doesn't have to be on integers. Okay. And actually, you'd be surprised. This kind of thing can be useful in when you're processing really large amounts of data. It's not that unusual to say, well, I need the data in pairs. This might be a function like this could be an intermediate step in a long chain of steps of processing data, where you have, these data items need to be duplicated, because you're going to do one thing to that version and one thing to that version. Because then another step might be a map or something that transforms this one way and this one a different way, then transforms this one way and this one a different way. So I want to transform each of these numbers 2 ways. So the first thing I do is create duplicates of them. That'll be one step of my data processing pipeline. And then the next step in the data processing pipeline might then go through and do another map on this and do something to that number and something to that number. Okay, so this is actually the key idea of modern programming. You build up big pipelines with little steps, and ML is a great language for writing little steps. And functional programmers think of big programs as made up of lots of little steps, and they write lots of little things like maps and folds, and then they chain them together to do the data processing. A lot of the big data is exactly this kind of thing. Maybe 10 or 15 little steps. Some data comes in, an answer comes out. In between the in and the out is 15, 20 little steps, where each little step could be a map, a fold, or a filter. And that's a very common programming paradigm. And it's becoming more and more common with big data processing. It's not the way you write GUI programs. It's not the way you write operating systems, but it is the way you write a lot of big data and machine learning stuff. Okay, and that's one reason why functional programming has become popular lately is, because it lends itself well to that style of programming. It lends itself very well to doing that kind of thing. And for example, Python is not considered an object-oriented, a functional programming language, but it actually is. Python was designed with functional programming in mind. When it came out and it was designed, most people didn't even realize that. But one of the reasons why Python's so popular with the big data people is because it's actually a baby functional programming language. It's got map and reduce and all this built in. JavaScript too. JavaScript's actually a baby functional programming language, so it lends itself kind of well to this kind of stuff. Like R, if you look at the R programming language, that's the language that's used a lot for big data. It's actually a functional programming language. Yeah, it's usually considered a statistics programming language, but it is, from the point of view of a programming language person, a functional programming language, and it works well with big data. Okay, so these little baby functions like this, this might look like something silly, but it's actually could be a very useful little step in a bigger program. Okay, now let's look at some examples that use folds. These are a little bit harder. Okay. Okay, first go over here and remember what fold, let's see, there's fold L and fold R. We're going to mostly use fold R. Fold R tends to be a slightly easier one to use. It takes in a function on a pair, an item, and a list, and produces a list. Okay, and the key is to go back and think about. Let's go back and look at the description we gave of folds. Okay, we haven't actually written anything with a fold yet. We derived fold, but we never actually wrote anything with it yet. Okay. Okay. The key is that when you take fold, you give it a function, an item, and a list. Okay. Now what foldr does is it takes that item and puts them together in the function. Okay, so it starts on the right with the initial seed value, the last item in the list, and it f's them with the function f. That gives you back a result here. Okay, that gives you back a result, and that result's fed into f with the next item from the list. So then you function those two. That gives you back an answer, and you feed that into f with the third item in the list. So you work your way through the list from right to left. So that's fold R from right to left. You start with this guy here, give it to F with this guy paired with him. That gives you an answer. That answer is paired with this. That gives you an answer. That answer is paired with this. That gives you an answer. That answer is paired with this in F all the time. Okay. Historically, what this was used for was summing up a list. Okay, so a real simple example of this, is fold R, okay, of the function x, the function on a pair, goes to a plus b. Okay, and you apply that to a list like, and you start with the initial value 0. Okay, then think about what that's going to do. Okay, it takes this guy and this guy and puts them into the function. So that will be 5 plus 0. That would be this first step here. Okay, so the B is the 0. 0 goes into B, 5 goes into A, and you add them. Okay. Now that answer goes back into B and gets added to 4. Then that answer that answer gets fed into B and added to the next item in the list. Okay. And it just kind of goes in and collapses this list by adding up the items in it. So the final answer is then going to be 2 plus and then 1 plus. Okay. So the classic, this was when they used to call it reduced. It reduced this list to its sum. Okay. So this is kind of the easy, or this is probably this is a really good example to keep in mind. When you're trying to sort out folds, remember this example. This is the thing that motivated folds right from years and years and years ago. It was a convenient way to say sum up a list. If I change this example just a little bit, I can take the product of a list. So if I want the product of a list, I would say, oh, fold the product function, but then I have to start with a 1 here. See, not a 0, because now I'm going to turn all these into products. And if I started with the initial value of 0, that's not a good initial value for products. The initial value should be 1. Oh, and I'm doing something subtle here. Fold technically takes a function, but almost everybody thinks of it as working with operators, because initially that's what it was. Initially, you would be folding the addition operator on that list. And here I'm folding the multiplication operator on that list starting at 1. But in fact, the fold is really, I mean, if I was really writing this carefully, it was f of 5 comma 0, then f of 4 comma 5 of 0, then it was f of 3 comma f of 4. Yeah, see, now this is getting harder to read, but this is what fold is really doing. Now it's f of 2. Okay. If you think about fold this way, it can be really hard to remember what's going on. It's almost everybody thinks of it in the operator notation. Okay, so there's what fold really does, this one here, but everyone thinks of it this way in the operator notation, because that makes it a little bit easier to think about. So people tend to think of it this way, okay, because and a lot of times your function just is take a, b, and apply an operator to them, okay? So in that case, it really looks like this. And historically, when people first started thinking about the fold idea, it was almost always folding a list using an operator like addition or multiplication. In fact, it used to be called reduce, because what they thought of is you're reducing a list to a single value. Okay, you're reducing a list to a single value, and people still a lot of times call it. It's still called reduce by a lot, like JavaScript calls it reduce. Okay, we're going to call it fold. That's the more modern way, because once you replace the operator with a function, you can do some much more powerful things than this. Okay, right. So the way to think about it is kind of keep that one in mind, and what you're doing is the 0 goes into B first, along with that one. That's this. Then that answer goes back into B with the next item in the list. That's this. Then that answer goes back into B. Notice that B is the answer of the last operation, and A is the next item in the list. Okay, so B is the result of the last operation. A is the next item in the list, walking from left to right. Okay, I'm walking from right to left. Okay, and you start off with this guy initially in B. Notice that it's full. These are fold R's. I'm sorry. Yeah, fold R. It's fold R. 0 initially goes into the right operation. the answer always goes into the right operand, and you're moving from right to left in the list. You start at the right end of the list. The initial value goes into the right end of the operator, and the items from the list go in the left side of the operator, but you move through the list from right to left. Fold L will do the opposite, kind of. Okay. Right. Technically, it's this, but that's a little bit harder to read. This is a little bit easier to read. Okay. But if you're, some people don't have any trouble reading this either. Yeah. So you can, either way is okay. You can think of it as either way. Okay. Right. Choosing the initial value can mean a lot. For example, if I put 12 here, what I'm doing is I'm adding up the list with a starting value of 12, which might be what I need. Or if I put 100 here, I'm adding up the items in the list, but starting with 100. Okay, that might be more useful than actually starting with 0. Here, if I start with 0, I'm kind of goofing up because the product of things with 0 is going to be 0, and I'm always going to get 0. So I really ought to at least start with 1. On the other hand, I could start with some other number like 5. That just puts a 5 at the end of the product, which is hard to think about why you would want that. It's actually kind of useful to think about starting with an initial value, then adding up all these items onto that initial value. So this is the initial value. With multiplication, you probably almost always would have a 1 here. Yeah, I can't think of many places where people want to multiply a bunch of numbers, but start with some initial number for the product. So if you're going to multiply a bunch of numbers, you probably want to start with 1. But it matters a lot what you start with. A fold can change dramatically what it does if you change the initial value. Of course, changing the function can have a big effect on folds, but surprisingly enough, when you do some tricky folds, changing the initial value can change the fold dramatically. There's some famous examples of how the function doesn't change, but you change the initial value and the actual fold is completely different. It's surprising sometimes how much the fold can depend on the initial value. Now, that's not the case with ones like this, where you're just folding a simple operator. But as we do a little bit trickier folds, we'll see that sometimes choosing the initial value can make a big difference. Okay. Now, there's one other real famous example of fold that you have to keep in mind. Okay. Suppose I do a fold like the following. I'm going to fold the cons operator. That's a function. Okay. Well, actually, I have to write it. It's an operator. So I have to write it this way. Op cons. Put the empty list here. Okay. Now, if I want, I can write that out more fully. I'm folding R. My function takes in a pair A, B, and what it does is it conses A onto, well, it's assuming that B is a list, so it conses A onto B. Okay. And then I'm going to start with the empty list, and then I want to do that to 1, 2, 3, 4, 5. Okay. Now, kind of go through the steps like we did up here. What's that going to do? The empty list goes into here. So I start with the empty list. The empty list is the initial value. It goes into here. Then I pull out the 5 and I put it here. So I'm consing 5 onto the empty list. That's my first step. Now that answer goes into the right, and I pull the next item out of the list and cons it on. So now I'm going to cons 4 onto that. That's my next answer. Okay. Now that answer goes into the B, and I pull the next item out of the list and put it in the A. So now I'm going to cons 3 onto there. And the next step is going to cons 2 onto that result. And the next one is going to cons 1, 1 onto that result. Okay. Now, all that's doing is that is returning me the list 1, 2, 3, 4, 5. Didn't do anything. Okay, now watch. If I go over here and give this to ML, okay. Oh, I didn't give it a name. So let me give it a name. I'll call it Bob. So function Bob equals that. Oh no, I'm sorry. Well, no, I'm not defining a function. I'm just applying fold. I mean, I could turn it into a function, but yeah, see, notice I folded on the empty list the cons operator on 1, 2, 3, 4, 5, and I got back 1, 2, 3, 4, 5. Okay. If I do it on a different list, if I do it on the list cat, dog, pair, I get back to my list. See, it doesn't do anything. It's actually doing something. Okay, it's rebuilding the list. Fold of the cons operator with the empty list just gives you back the list you started with. Okay, now what this shows is that fold is actually a generic way to traverse a list and do something to the list. It's actually, this is why fold has got this universality to it. It's glorified for loop. It's a abstract functional for loop that lets you process a list and do something to each item in the list. And here I'm seeing that I'm just I'm iterating through this list and rebuilding it. Now, if I actually wanted to do a little bit more to the A here, I could do something to the A just before I put it back in the list. So it's actually letting me iterate through the list. If I make my function here just a little bit more complicated, I could do something to A before I put it back in the list. So here's an example. This is actually one of the homework problems. I'm going to, oops, I'm sorry. Just before I put A back in the list, I'm going to do something funny to it. I'm going to make it a dupe of itself. See? So what I'm going to do now is take an item from the list and what I've gotten so far, and I'll take the item and duplicate it in a pair and then cons it onto the list so far. Okay. See, it duped the list. So now I got 1, 1, 2, 2, 3, 3, 4, 4, 5, 5. Fold, this is the beauty of it. This is the real powerful thing. Fold is actually not reduce like people thought it was up here. Fold is, at some point somebody figured this out. Fold is actually a very powerful abstract way to iterate through lists and do things to the list. But a fold operation is essentially stepping its way through the list, one item at a time, letting you do something to the list. Now, you could rebuild a list after you process the item, or you could just add the results together. You can do anything you want. But what you think of is you're iterating through that list and doing something and accumulating an answer. As you iterate through the list, you're accumulating an answer. And at the next stage, you get to use the thing you've accumulated on the next item. Then you get to use what you've accumulated on the next item until you've gone through the whole list. It's a glorified for loop, a very powerful glorified for loop. And that's why it's gotten this reputation. I pointed out the other day, there's this idea of the universality of fold, because it really just is for looping, but in a very controlled way. If you think for loops are easy, I've mentioned this before in class. I think brought it in this class. For int I equal 0, I less than or equal to 27, I plus equal 3, I plus plus, I minus minus. Now tell me how many times that thing loops. For loops are nightmarish. For loops are a really bad idea. If you were inventing programming languages today, you might say, no, we're not going to put any for loops in our programming language. You're taught to think in terms of for loops. They're really horrible. How many times does that thing loop? Who knows? You're counting by threes. It matters whether you do that or that. There's too many weird things you could do in a for loop to goof up. You have to worry about, where do you start? How do you end? How much do you increment by? What happens in the body of the for loop that might affect the for loop? I mean, I work with a lot of students and help them debug their code. A lot of bugs come up from people doing something in the middle of a for loop that's actually affecting the bot of the iterator of the for loop. You can accidentally get feedback between what's up here and what's down here, sometimes in very subtle ways. Okay, for loops can be really nightmarish. Folds are a way of controlling the iteration in a way that gets rid of a lot of this bugginess in fors. That's one way to think about folds. Now folds only fold on lists. So for loops, in a sense, for loops are way more general than folds. For loops are more general than folds, but folds only work on, they iterate through lists. But when you can use a fold, it's actually a better idea. A well-written fold, you can state mathematically that it's correct. That's actually what they've realized. Fold is a minimal, fold can be analyzed from a math point of view. It's a well-defined thing. You can write theorems about folds. You can't write theorems about for loops. And that's actually one of the big goals, is to be able to prove that programs do the right thing. If a program's written in terms of folds, you got a better chance of, being able to prove that it's doing the right thing. Okay. All right. So let me save that. Okay. So initially, think of fold that way, as an operator. Just kind of working its way from right to left, doing an operator on those two, then those, then those, and those. Okay. And then you start thinking, okay, as a function, it means feed that initial item into the right of the function, pull out an item from the list, put it in the left of the function, do the result. Then that result goes back into the right of the function. Another item from the list goes into the left of the function, do the calculation, and then that result feeds back into the function. Okay. And then eventually you kind of think of it in terms of, it's really kind of an iteration. You're iterating through the loop, you're iterating through the list, you're accumulating results as you go through the list, and you could do anything you want with, here's the accumulated value so far, here's the new value. Okay, so the B is what you've accumulated so far in the list. The A is the next item in the list, and then you decide what to do with them. And that's going to be the new accumulated value. Okay, so you're iterating through a list and accumulating a value. And it's fold R because you're starting at the right end of the list. Fold L just means you start at the left end of the list. Okay. Traditionally, people tend to write more fold R's than fold L's. I'm not really sure why. So I'm just kind of emphasizing right now fold R, because that's kind of sort of the one that people use more often. Okay. Now let's go and look at some of the problems. We just did one of them. Okay, here's the list of problems. Okay. Okay, this is the one we just did, dupe list. Okay, so dupe list is, where did I put it? Is it this one? Yeah. So to make that a function, dupe list on x's is dupe list on the x's. See, that makes it a function now. Okay, to duplicate the items in a list, I'll fold the function that takes two items, dupes the first item, and consts it onto the second, because this is the accumulated value so far. I'm accumulating a list. I want to take this item, duplicate it, and add it to the list so far. Okay, so dupe list on x's is a fold R of that function, starting with the empty list on the x's. Okay, and then I can just check. Oh, let's see. Now there's a test case. Okay, so take this, give it to ML as a function definition. Okay, and now check that it does what we want. That it dupes the item in the list. Oh, wait a minute. Oh, no, I'm sorry. This one's a little bit different. This one doesn't dupe them as pairs. This one dupes them as individual items. Anybody see what I need to change? So the one I did is not quite the right answer. See, I'm supposed to not dupe them as pair. I'm supposed to dupe them as 1, 1, 2, 2, 3, 3. Does anybody see what do I change over here?
Instead of having the pair A to A, con down to B, you can have A, con down to A, con down to B.
Yeah, just replace those as just replace that comma with a cons. Okay, there. A cons on to A cons on to B. Okay, that'll accumulate two A's in front of what we have so far. So that'll accumulate two A's in front of what's so far. So that's the one I want for this. So that's a slightly different one than we did in the other page. So there's our dupe list. Okay, and then let's do the test case. Okay, boom, true, got what we wanted. Okay, if you want to see the result, so you can just see it duped it. Okay, let's do a little bit harder one. Okay, use fold one line. Okay, a function that takes a Boolean list and returns an int. Okay, and it's supposed to count the number of trues in the Boolean list. It's supposed to count how many trues there are in here. So true count takes in a bunch of it takes in a list of one thing, notice that I don't use pattern matching when I write this kind of code. That's a bunch of X's. Notice how the fold doesn't use pattern matching. It just says, here's how you fold the X's. Let's go back to this one, do one other thing. Let's write this function recursively. Okay, function dupe list. We can go back and treat this as a function from something like an earlier homework assignment. Function dupe list. What happens if you give it an empty list? Well, if you give dupe list an empty list, it should give you back an empty list. Okay. On the other hand, what does dupe list give you if you give it a non-empty list? So something const onto the other. Well, in this case, you take X and you cons it onto X, const onto the recursion of dupe list on the rest of the X's. Okay. Now, notice here how I'm using pattern matching, because I have to say, well, if you give me an empty list, I do this. If you give me a non-empty list, I have to tell you what to do on the item that's at the front of the list. Duplicate it on the list. Notice that when I do things foldy way, I don't even need to know, I don't break up that list. I just say fold it. Fold processes the whole list. The recursion is in here. The fold is where the recursion is now. Instead of me writing out the recursion, fold. This is another reason why I think people call this higher order programming. The recursion is now buried in this thing. I'm using a higher order function, a more sophisticated function. It does the recursion for me. In fact, if you look at really modern functional programming, it isn't recursion, it's how do we avoid using recursion? The real goal of modern functional programming is to do as much as possible with higher order functions that do the recursion for you. you're really trying to avoid the recursion. The recursion is used for the library functions, and you should use the library functions that do the recursion automatically. That's one of the goals of ultra modern functional programming. The library functions should be the ones doing the recursion, and you hopefully can write your functions using the library functions, and you don't need to do recursion anymore. Now, that doesn't mean you don't need to learn recursion, because everybody has to understand how these library functions work. But we're trying to see here, this is written recursively. Now I can go over here and punch that in, and it'll work the same way. Okay. And I can test my test cases. See, it still works. I'm using the recursive version now. Okay. Sometimes it's more efficient to write the directly recursive versions. Just like anything in libraries can be convenient to use, but sometimes when you use a library, it's not as efficient. It's not as finely tuned to the problem as if you write your own code. But at the same time, if you use a library function, it's been debugged. If you write your own code, you got to worry about introducing your own bugs. Now, in this case, this is not more efficient than this. I think we'll see an example in a minute where the directly recursive one would be faster than the library use of fold. Okay, but you can always write these things directly yourself in terms of recursion, but the goal here is to say, well, I can write this as a fold. Okay, now over here, let's do true count. We're going to write this as a fold R of some function on some initial value of the b's. Okay, now we have to figure out what should the initial value be and what should the function be. Okay. Okay, the function is always going to be the same thing. It's a function of a pair AB. The B is the accumulated answer so far. So B is a count of how many trues we found so far. A is another item from the list. It's a Boolean. So what we want to do is we want to say if A. If A is true, then 1 plus B. Add 1 to the B's. Else, well, we didn't find a true, so just don't add anything to the B. Okay? Remember, accumulated results so far, new item. We're supposed to count the trues. So if we got a true, add 1 to the accumulated results so far. Otherwise, don't add anything to the accumulated results so far. What should be the initial thing?
Zero.
0, because at the start, you haven't found any trues yet. So start with 0. You haven't found any trues yet, so the initial one should be 0. Okay, let's try this. Okay, it compiled correctly. So true count. Did I spell all those right? So are there 4 trues in there? 1, 2, 3, 4. 4 trues. Okay. All right. All right. So, notice how the thinking goes. It's a glorified kind of iteration. You're iterating through the list from right to left. This is what you've accumulated so far of your answer. This is the new item in the list. How do you build the next answer? Okay, with your accumulated answers so far and your next item, what do you do to build the next answer? And what should you start with? Okay. Okay. Now let's do member. How much time? Let's do member, because this is one that's interesting. This is one where it's going to turn out that the fold version's inefficient and the direct recursion would be faster, but the fold's still nice to know. Okay. Member takes in an item and a list and tells you whether that item is in the list or not. So it returns true or false. So here's a test case. Member 2 in the list should equal true. Member 0 in the list should equal false. There's a couple test cases. Okay. All right. So it's okay. Member of an X in a list of X's. So we're asking, is X in the X's? We're going to write it as a fold R. So we need to fold some function onto some initial value on the X's. Okay, notice I haven't used the X yet. Okay, fold some function with that initial value on the X's. Okay, now the function takes in a pair and gives me out. Now I really start thinking. B is my answer so far. That's either a true or a false. Either I found X or I haven't found X. Okay. And A is the next item in the list. Okay. If A is X, then we'll return true because I found it. Else, well, if I didn't actually find X here, maybe it was found earlier. So return the previous answer. See, if I didn't find it, then go ahead and say, well, here's what's been figured out so far. Okay. So if I find it, I return true. And if I don't find it, I'll return whatever's been given to me so far. And at the beginning, of course, you haven't found it yet. So the initial value is false because you haven't found it at the beginning. Okay. All right, let's check. Let's check this. Yeah, I get a warning calling poly equal. I think that's come up a few times before. Don't worry about it. It's just a warning. It's because we're writing this in a very generic way. We didn't say what X and X's are, so ML has to work harder at doing this. What it's warning you is that equals is an inefficient equals. It's the polymorphic equals. And it's really warning you that that's a very slow operation. Are you sure you want to do that? The way you could speed it up is you could say that X is a int list. Okay, so for example, suppose I say that, not X. Well, yeah, say X is an int. So everything's an int now. Now ML says, oh, that's an int, that's testing ints. No more poly equals. Now the function is no longer as general. The function now is not a polymorphic function. See, no more warning, but no more polymorphism. The function takes in, it searches for an int in an int list, but it's more efficient. This one's polymorphic. It tests for any A in an A list, but it warns you that a polymorphic comparison is slow. And it's warning you saying, if you don't need the polymorphism, don't use the polymorphism. If you're really only ever going to test integer lists, specialize the function to be on integers. It'll be faster. So that's the motivation for the poly equal warning. They're just kind of telling you that if you don't need the polymorphism, you'd be better off specializing the function to be what's called monomorphic. Now it only works on one type, int. It won't work on strings. It won't work on doubles. Okay, so that's where that warning comes from. Okay, we're going to leave it generic. We'll leave it like this. Okay, now we can check it. I happen to be using integer lists here, so I can go ahead and use my monomorphic version. And we really do use words like monomorphic and polymorphic. Okay, that one was true, and this one should be false. Notice that the answer is false because the result, this was false because this one gave false, which is not true. Okay, yeah. If I want, I put a false there, and then the result is true because I got the right answer. Okay, now let's write this function recursively. Fun of member. Okay, if I ask for X in an empty list, in fact, it doesn't even matter if it's X. If I ask, if anything, if this guy in here, the answer is no. Okay. Okay. Nothing is in the empty list. Okay. Now, member X in a non-empty list. X in front of, well, I can't use X again, so I'm going to write this Y in front of Y's. Okay. I want to know if X is in this list. Well, the easiest way to do that is to say if X is Y, or I mean, right there, okay. If Y is X, then true. Else, well, keep looking. Else, member X in the Y's. There's the recursion. Okay. If I find it at the beginning of the list, just stop. If I don't find it at the beginning of the list, continue recursing through the rest of the list. If I get to the end of the list, I didn't find it. Okay. Now, check that one. Again, I get the polyequal warning because I'm doing a polymorphic test of equality. Yeah, again, I could specialize this to say that X is an int, and then it's not polymorphic anymore. And that makes it more efficient, but I'll leave it polymorphic. Okay. Then my test cases. Okay. Now, think about the following test case. Okay. Think about the recursive one. Right away, it finds 0 at the beginning of the list. It returns true, and it never recurses through the rest of the list. This one actually stops as soon as it found that item. Okay. Actually, let me also put a 0 here. Now look at the fold R. The fold R starts off by saying 0, that goes here, okay, and then asks, is it equal to this 0? This 0 goes there. That's the initial value, okay? And it says, oh, yes, there's a 0. But then fold R continues to go through the whole list. The fold R is not going to stop its recursion as soon as it finds, it has no, fold R doesn't know to stop. Fold R, unless there's some trick that I don't know about, fold R goes through the whole list, okay? So this is its, maybe you can say it's one little disadvantage of it. It will go through the whole list. Whereas, see, this recursion, it's got the, it's written in such a way that as soon as it finds the item, no more recursion. So if the item were in the middle of the list, it stops there. It'll check this, check this, check this, check this, check this, find this, stop the recursion. See, there's no more recursive calls when this is true. You just return. There's no recursion there. The recursion is only when you don't find it. So this thing, the recursive function would only iterate this many times. Fold is going to iterate that many times, the whole list. Okay? So you can make the case that there are times when you might be better off not using fold. You'd be better off writing your own recursion. Now, people are well aware of this. And the ML is a slightly older language. There's a language called Haskell that it's that one book I pointed out from that one publisher is a famous book on Haskell. Haskell actually solves this problem. Haskell's fold can be stopped in the middle of doing the folding but it involves something very sophisticated called lazy list processing. And it's a very advanced topic, and it's not, and it's got some problems. It's kind of a good thing and a bad thing. The Haskell is what we call a lazy language. If you Google Haskell is lazy, you'll find out that, faster code with laziness, lazy evaluation. What is a lazy programming language? Essentially, what lazy is it tries not to avoid, it tries to avoid evaluating things. So in fact, the lazy fold sort of notices when there's a certain trick to it that it can see that it no longer needs to continue folding. Okay, but it turns out to be not an easy idea. So, but one of the reasons why Haskell is lazy is because they want you to use fold, but they don't want you to pay a price for using fold. See, here we paid a price for using fold. Well, paying a price for using fold is not a good thing. We should get what the guy who invented C++ calls them free abstractions. Okay, you should get no, he calls them, this is kind of a neat idea. The guy who invented C++ calls them cost-free abstractions. Okay, he calls them zero cost for abstractions. You should be able to use an abstraction like fold without paying a price for it. And the guy who invented C++, that's his one design goal, is that if the language has an abstraction, you never pay a price for using it. In the case of ML, if you use a fold, which is an abstraction, you might pay a price for using it. The fold might go through a whole list when it doesn't have to. Like here, the recursive one stopped right there. It didn't go through the whole list. Fold will. Haskell tries to give you real cost-free abstractions, but to make fold cost-free required inventing this idea of laziness. It does a lot of other things for you. Laziness is is interesting property. It's also very controversial. Some people think it shouldn't be in the Haskell language. Some people think it should be. It's actually very interesting. It's still like an open thing whether laziness is a good idea or not. A lot is written about this. Is lazy a good idea or is it not a good idea? It does make some things more efficient, but it also can make programs hard to analyze and understand. But it does solve this problem with fold. It will make the fold stop when it doesn't need to do any more folding. Okay. All right. So we've done some fold examples now. Hopefully, we ran out of time. On next week, we'll if there's any questions about the homework, but hopefully this gives you a sense of how to think about those fold examples in the homework. Remember, think about it. What you've accumulated so far. Next item, what to do with the, to build the next result. What you have so far. Next item, what do you want to do to build the next result? Okay, think of folds that way. Anybody got any last second question? Any question at the end?
Are you going to be available tomorrow by any chance to meet?
I got several meetings. I don't know what, it depends on the time. I've got like 2 or 3 meetings I got to go to tomorrow. So send me, if you want to meet tomorrow, I can try. I think, I don't even remember the time. I do. I'm very much a just in time meeting person. I'll look up the times of the meeting in the morning. As long as I wake up early enough. I don't even remember what time the meetings are. I think they're in the morning, I think.
Okay. I can pretty much do anytime tomorrow except for 3 to 4.
Okay, send me an email. And yeah, I have to look up what time my meetings are. I think I'm done by maybe like 11 or 12, maybe even by 1 or 2. I know the meetings I think are earlier in the day. Okay. So but yeah, send me an email. That's the best thing to do. And we can arrange a time. Okay.
Okay, that works. Thank you.
Okay. Anybody, any other question about this stuff? Any question about folds? Any questions? Folds are tricky. Folds are really pushing the envelope of interesting kind of thinking. Once you're used to them, they're kind of clever. But they do take, they're compared to writing for loops, I mean, they actually look harder than for loops, but in the long run, they're easier than for loops. But initially, you kind of wish you could just go back to writing for loops. but in the long run, folds are a good idea. Okay. All right. So we'll quit there. I'll put these ones that we did up on the course website. So these examples that we just did, I'll put them up there, and then you can use them as hopefully a little bit of a template for studying I mean, there's examples in our textbook too. The textbook does several of these, more of these, and you can use the examples in the textbook and these hopefully as a template for solving out the problems in the homework assignment. Okay. Any last question? Okay, so I'll stop sharing, and okay, have a nice weekend. Bye.